If you are going to do any kind of astronomy, you will eventually knock up against the idea of apparent magnitude, which is a measure of how bright things appear to be to an observer on the surface of the Earth. The aim of this video is to show you just how useful apparent magnitude can be when it's handled correctly, because we can get a measure of how much energy is arriving from a celestial object onto the surface of planet Earth. The ancient peoples of planet Earth were very good observational astronomers. One thing that they'd worked out how to do was to compare the apparent brightness of stars in the sky. As their system developed over the years, it became known as apparent magnitude. Let's clear up the word intensity. This means the amount of energy arriving per metre squared per second at the surface of the Earth, and is therefore measured in watts per metre squared. The star Sirius is the brightest star in the night sky, yet despite this fact, it still only delivers a vanishingly small 1.1 times 10 to the minus 11 watts per metre squared. As the need for accuracy developed, so it became clear that a better system than "I doth declare this to be a magnitude 1 star, my lord," was needed. And so, during the 19th century, the scale was accurately redefined using logarithms. Here's the definition now. A magnitude 1 star has an intensity 100 times greater than a magnitude 6 star. This in turn means that for the magnitude 1 star there is 100 times more joules per second falling on a metre squared than for the magnitude 6 star. This means as we go from magnitude 1 to 2 to 3 to 4 to 5 to 6, we are in fact going up in 5 steps. And we therefore need to know what number we raise to the power of 5 to get 100. Taking the fifth root of 100, we find that it's 2.51, and so this means, unsurprisingly, that if we raise 2.51 to the power of 5, we get 100. Well, so what? This means in effect that if we want to know the ratio of the intensity of two stars, I2 over I1, then roughly speaking it's going to be 2.51 to the difference in the apparent magnitudes of those two stars. In this example then, I2 over I1 is going to be approximately equal to the magic number 2.51 to the power of minus 5, and if you work that out, therefore star 1 is unsurprisingly 100 times more intense than star 2. As we've seen, the problem with apparent magnitude is that it depends on the distance, because obviously the intensity that arrives at planet Earth drops off as an inverse square law from the star. In order to solve this problem, a more refined system called absolute magnitude was developed, which only depends on the luminosity of the star. The word luminosity is used to describe the amount of energy radiated from a star. This is obviously of the form of electromagnetic radiation. For stars such as our Sun, this figure is, as you'd expect, absolutely enormous, of the order of 4 times 10 to the 26 watts. Absolute magnitude is the apparent magnitude that a star will have if we bring it to a distance of 10 parsecs from planet Earth. In other words, if you want to compare the absolute magnitude of, say, two galaxies, we imagine what their apparent magnitude would be if we brought them both to the same distance of 10 parsecs. This is great because we have effectively removed the variable of distance from our comparison of magnitude, and it enables us to make much more meaningful comparisons.